So yes, thank you very much for inviting me today, and to Sam, to you, to organize this event. It's a winter, so it's a bit cold, so I hope people will warm up a bit. And I appreciate in fact the very good technical quality of HKML over the years, and that's one of the reasons I decided to try to join the activity and opportunity, in fact, to have open discussion with the members, to have some discussion and to maybe some members probably have some good technical background and to exchange on some topic. I see this presentation much more as an exchange, rather to be focused on very specific point. So I worked in financial industry in the past, BNP Paribas, Merrill Lynch, blah, blah, and ING. So I'm pretty familiar with the kind of stochastic modeling and things, and I did a couple of talks on that topic. And now I'm working much more in the big data, machine learning in Japan, and mostly in the ad and recommendation. And as a principal machine learning engineer, I was previously in the very large e-commerce in Japan with a lot of Japanese customers and a lot of high billion items, quite big. And now I'm working in a company called MyBot since last year. It's focusing on geo-spatial data and more specifically on ad recommendation. So MyBot is a company specialized in geo-spatial map provider for company, typically for Amazon or a kind of a big company. They have a lot of maps. They have a lot of users. Probably you have probably used one time the map without knowing it was maybe MyBot. And the MyBot in Japan is owned by SoftBank. SoftBank is the number 2 telecom in Japan. And they develop a lot of geo-tech solutions for corporate. And I'm in charge of the machine learning for the geo-ad part. So I will focus more of this talk about this advertisement and recommendation part. So quickly, the goal of this talk is to highlight some key part of machine learning, more focused on reinforcement learning part, applied to ad and recommendation field, and to be a bit more focused on the reward, on some practical issues of applying machine learning and reinforcement learning. And to try to bring a bit different perspective and to share some bits of personal experience in that field. He also has mentioned before to exchange with the members, either the technical or the less technical part. So that's a bit the part. So there are a couple of slides, maybe too long, so I will skip some of them. I will try to focus on some specific one, which is probably much more interesting for discussion and to examine more in details. So I will start with the overall principle on reinforcement learning quickly. I highlight some application overall, especially the main challenge. Why, in fact, reinforcement learning is good, but also very challenging. And that's why I'll explain a bit what is a Stochastic Bandit, which is a kind of subfield of reinforcement learning that people use in advertisement and recommendation. Why, particularly why people use Bandit and not the full reinforcement learning part. I explain a couple of example here and evaluation method too, which is quite interesting. And the third part, highlight some key challenge in doing online more in the apply. When you try to use machine learning at a larger scale, you have a ton of problem coming that you don't really expect, especially the scaling, the latency, all kind of things that you need to take into account because it's a real world application. We highlight a specific part on geo-spatial data, just to raise awareness. And after some discussion, some presentation about actual applied research in that area, the recommendation, a bit of personal opinion if we have time. Okay, let's jump into. So I just recall quickly overall what is a machine learning algo. In general, is You have some kind of learning process with interact with the data or environment. You have some kind of optimization process, mostly the gradient descent, not always, but mostly. And at the end, you end up with some representation part. It can be some weight, it can be a tree, or usually it's kind of pseudo program. And within the representation part, you can do some tasks. Typically, predict something or now generate some whatever things, like ChatGPT generate some text. You have some output, and we can reuse the output to have some feedback loop into the environment. It's called intervention. It's a causal language. And this feedback loop is what is used for reinforcement learning. We have feedback loop back to the environment. So this is the template. And I just would like to have few words about the learning process because usually learning is not really kind of a bit overlooked term. So learning, in fact, probably for the people who came from machine learning at university, they learn that it comes from path learning. Path learning is a kind of formalization of machine learning. Formalization of the learning, what is learning. And path learning means it's probably approximate, correct. So probably means approximate means it's a bounded error. And probably is a high probability. So learning has a clear kind of mathematical formalization. It's done a very long time ago by less variant, and it's a term that usually people use it or because they use machine learning, deep learning, but it's not a term really that people define. In fact, it has a clear definition. And just to go a bit few words about the learning, you have many ways to learn things. And the typical way is called supervised learning. We have some input, we have some label, and we try to find whatever model to predict the label. So, and the main challenge is to find good label. It's the main challenge. In the real world problem, sometimes we don't have label, so we try to find labels. And you have another way, the clustering with unsupervised. You don't have label at all, and you try to find some pattern. And you have self-supervised learning, is NLP, the whole language model, the chatbot. You try to have invariance in the data, find some stable pattern directly in the data, and to try to learn from the patching. And our case, the reinforcement learning. Reinforcement learning has another name, it's called control learning, depending on where school people are. And you have a state action feedback. And you have a lot of different type of learning, differential learning for privacy data, meta learning. Transfer learning is very important topic now because a lot of language model and vision model are focused on transfer learning because big model to the smaller model. It's quite very important step. Adversarial learning and graph learning and structure learning. So mostly you don't have one way to learn from the data. You have many different ways to learn from data. And each way has a pro and con, and each way has some kind of mechanism to extract the information. So I think personally, this problem is the most interesting slide for that presentation, but in something probably you cannot find. I did not find this kind of slides on a conference on internet, so it's kind of a bit very specific, but it's interesting. So to come back to reinforcement learning, so reinforcement learning is a learning process where we interact with the environment dynamically. Opposite to supervised learning, you have ORAC, usually human people, who select the sample, this is the ground truth, and please fit. So you have two mechanisms. One is action. So the model provides some action as output, and the action will do some intervention in the environment. And because of the intervention, we get some reward. It can be cash, whatever we want. Yeah, at the same time, we have also observation, like passive observation of the environment. So we have a kind of feedback loop, which is very dynamic process. That's why, yes, let me just, yes, okay, so I have another slide about, maybe I will talk after, okay. So for the reinforcement learning, the one of the issue of the reinforcement learning is a very, very large field. It's much more larger than people think because there are many schools in reinforcement learning. There are two main schools. Is model-based reinforcement learning. It's called stochastic control, optimal control. Is usually learned at in class university. Is typically Bellman equation, stochastic optimization, including dynamic programming. It's called model-based. You have another one. It's called model-free. We don't have to explicitly model the environment. It's typically the back in general by neural net, not always, but like AlphaGo, Zero, or lot of game problem. And you have for each of the school, you have different way to do the formalization. And people sometimes are very deep, and it doesn't touch each other, so it's kind of very large field. So okay, so let me go into quickly in the formalization. So the most important part in the reinforcement learning is to find a policy. A policy is called decision algo. The decision algo is you want to find some action, the probability of some action, given some state. So you have some state of the action and you want to find the probability of some action. So this is a goal in front of reinforcement learning. In order to achieve this goal, you have some kind of reward function. It can be cash amount in dollar or click in advertising. And you have the total reward, which is the sum of all the discounted future. So you try to have a model model of the reward of the future, and you try to sum all of them. And this is the total reward, and you will use this one to guide the learning process. So you have a bit of technical terminology specific to reinforcement learning. You call the state value. The state value is just the expected reward given some state. And the action value is called Q, is the expected total reward given some state and some action. It's almost the same thing, but you are a bit more precise. As I said, the goal of reinforcement learning is to find some policy, decision algo to maximize this expected total reward. So you have a dual formulation. So it's to find the optimal policy for all possible future paths. That's the generic problem on reinforcement learning. On top of it, you need to add assumption to make sure that we can do the math a bit more correctly. Especially, you need to add the Markov property, so it become MDP problem. And that means that the problem is if you have all the data in the past, you only take the last one, the time t, and you can do decomposition. It's called Bellman, which is that the best, the optimality is the sum of the current one and the discontinued future one, some kind of decomposition. So you do a bit of math. If you go into literature of reinforcement learning, you can find many approaches. Only got two main ones that you can find in textbook or in general. One is called Q-learning. So we directly approximate the Q value, which is the expected total reward based on the state or action. And directly how we approximate, we need a simulator. Typically, we need a game simulator, Monte Carlo simulator, whatever simulator. And we can approximate using the neural net or whatever things. But mostly it's based on simulation. And you have the other one, it's called policy gradient. So we learn directly the policy instead of learning the expected total reward function. We learn the policy. There is a policy gradient, is a theorem in the field that can do some much more easier computational process. So you have those two, what you learn the policy gradient. And you have a lot of others, interpreting everything. So I skip those one. And I will go into the application and main challenge, which is probably the most interesting. So you have three or four main applications. One is typically either in game, in robotics, or in physics simulation. All of them are simulation based, like AlphaGo, AlphaZero, robotics too. you need a simulator to generate high number of samples because reinforcement learning is quite inefficient for learning. If you have a simulator, it's very easy to get sample. You Monte Carlo everything and you get as much sample as you want. It works because you can get a million of sample. If you have enough compute, probably you will converge at some time after 10 days of training or 20 days of training. The other application is works well. This is the kind in this way, it's like black box optimizer. Reinforcement learning has a good capacity to explore very high dimensional problem efficiently, typically alpha zero. So it can be used as a black box optimizer, like CPU design. This one is used actively. Now in molecular design, all the pharmacy. You can check, there is one startup is called InstaDeep. They are specialized in this kind of topic. So it's the alternative of the global black box optimizer and it works relatively well, but it requires quite some expertise. Okay, so, yeah. So people can check on internet. And the part which is more focused on today's talk, which is the online recommendation, we take some dynamic decision to show some advertising to some user. User click or doesn't click, and based on this, we show another advertisement. And we have also trading execution, a lot of financial part also that I forgot to mention. So this one is important. So my today's talk is to focus more on the application of online recommendation and how we apply this. Okay, let me go. Yes, application. You have when you go on the website, you see the headline news on website is mostly kind of reinforcement learning. I go typically for advertisement, pretty sure. You have Apple Store. If you go on the iOS and if you download some app, you have the recommendation for the app. You use called two-layer bandit. It's like a two-layer reinforcement learning algorithm. If we go on Facebook News, they use some form of reinforcement learning between reinforcement learning and bandit. People can share. They have a library called reagent. And those one and yes, this is those main application. Everything you see on the front page of the website, especially Netflix on Amazon, probably you have high probability that it will be bandit or reinforcement learning application. So as one advantage of reinforcement learning than other one.
Okay. Just a quick
Yes.
naive question from me. So
Yes.
to optimize pages and so there were lots of techniques related to A/B testing before. So is that like suboptimal compared to the Bandit approach or
No,
Bandit?
A/B testing. Yes,
Okay.
yes, good question. Yeah, thank you for the question. It's a good question. I will mention a bit after. Technically, A/B testing is just to test if algo A is better than algo B. So we have 5 algo A, B, C, D. We don't know which one is the better. So we just run all of them in parallel. The A/B test, the experiment, we say the algo A is better. That's the A/B testing. Each of the individual algo can be bandit or reinforcement learning. So A/B test is just doing the experiment.
Okay.
Yeah,
Thanks.
after you have a bit some technicalities, but I will probably explain a bit after. But I think it's a very good question. Mm. Yeah, and so just to come back, so one benefit of reinforcement learning is handle better non-stationary environment because you have the dynamic process learning. You do some action, reward, and in general is handled better because you have dynamic process. Usually you have issue of overfitting in supervised learning typically, and underfit sometimes if you have a simple model. And main challenge, in fact, why we don't use just reinforcement learning instead of just supervised learning, because in fact, the constant reinforcement learning, the general algo, we need to access to massive data sample. Typically, we need a simulator. You have currently inefficient learning process. You have a lot of technicalities due to this. And also, we have another issue with reinforcement learning. We need to have a correct modelization of the agent state and environment reward. Sometimes the state can be incomplete. And for real-world problem, the modelization can be complex because sometimes we don't know the state, we don't know what's the reward. Reward engineering can be very complex because you can have a lot of non-stationarity and it's typical issue. And another problem related to this is it's called the credit assignment, that when you do some action, you need to assign some reward. So when we have directly the reward 10 minutes after, 1 hour after, of course, we can assign. But suppose the reward is 1 day, 1 week, or 1 month after, you don't know which action you have taken. You don't know exactly which action is the reward is related to which action you have taken over 1 month, for example. With very long sequence of action. So this one is can be complex, especially in real world problem, because it's not necessarily obvious. A last one, which is the case of advertisement and recommender, is high cost at training, but not only at training, but at inference. It doesn't fit in low latency environment very well. A supervised learning has one benefit is training efficient in general. We can control better because we control the label. So we can try to fine tune in some way for kind of quick training, supervised efficient. So that's why especially for the cost of inference, I will explain what is a bandit, which is address partially some of those issues. Let me go on the next slide. Sorry. Okay, so technically, Bandit formally is a reinforcement learning, but we assume the agent state is constant. So we simplify the problem a lot. Main reason is to make things computable, mathematically easier, that we can have a mathematical boundary. And second step is also faster for compute. So we only focus on the action and reward. So we only assume that we take some action and we get some reward. And in fact, in Bandit, the vocabulary are a bit different. They call action arm. The reason why Bandit theory has been developed outside of reinforcement learning school field, so they develop their own vocabulary. So if you have a look at the research paper on Bandit, the formalization and notation are different. And second point, the Bandit reinforcement learning, even they are both reinforcement learning, they are different domain application. Bandit is typically used for the online advertisement and recommendation because it's much more compute efficient. We just focus on action and the instant reward. Another benefit of Bandit has we simplify a lot the assumption, the policy. We can prove we can have mathematical bound on the policy, so it's useful in critical system or in other area. So the goal is same. We want to find policy to maximize the total reward, and we are only interested in action. We don't care about the state. So we only try to model how much this action provides the reward. And also, we don't take into account the future reward. We just take the most of the time only the instant reward. I show this advertisement, is user click or not, something like this. And there is another concept in Bandit that people use is the total regret. So total regret is technically we can prove the existence of optimal policy in Bandit assumption is the difference between the reward between the best policy and the current one, the one you are using now. And just with some difference over all the period. It's for the total regret. Is a measure of the one exploration and one exploitation over time. Technically, it calls the number of mistakes you make over time. It's a good measure to compare algorithms between them, technically. And another benefit that in by using this formalism, and because we have simplified a lot of assumptions, we have asymptotic bound for the bandit. So the optimal policy, we have the regret in logarithm time, means that on average, the best policy will not make more than logarithm of the unit of time mistake, the best policy. This is the lower boundary. And of course, we want to, for each of the policy, I got a couple of them, something. We can calculate the upper bound. Some of them are linear. The bad one are linear. And the optimal one are between linear and logarithm. So that is, for the research perspective, a lot of people spend a lot of time to optimize those upper bound. So we introduce another concept of bandit because people remove the state in the bandit, but we need to introduce back the state. They call it contextual bandit. Is to fill a bit the gap with reinforcement learning because at some point we need to have some state. If let's say the environment is very non-stationary, we need to have some state, especially the reward process need to have a more complex modeling. So technically, they add some kind of pseudo state, not to the agent, but to the reward. So technically, the expected reward is conditioned to the context, some context vector. Technically, the covariate vector, you can say time, location, whatever embedding, whatever covariate. Just make it more realistic. Sorry.
So quick question. So in your experience, it's better to have this vector of covariates and learning one model, or maybe do a regime switching model like HMM or something else and fit one bandit per regime?
Yeah, that's a good question. It's what people are doing. I'm not taking maybe a regime in my work. I never investigate myself. Is what people are doing? They use to have a context vector. Probably is maybe easier for feature engineering because we can put as feature as you want in the context vector. Technically, you can put embedding, time, location, whatever thing you want. So you have a bit more flexibility in terms of the covariate. In the regime switching, you need to render different model. Technically, you can have one model to the regime switching, but you render different model as well as maybe from practical point of view, maybe add more effort. In that case, people just add more input feature in the covariate.
Okay.
So usually what people are doing, probably that's the reason why.
Thank you.
Okay. And so to come back to your question, the one that mostly people use in advertisement and recommendation is called Thomson Contextual Bandit. So in summary, the expected reward, the conditional expected reward, condition to the context is just a linear form. Context vector times some weight vector. And usually the weight vector we put a Gaussian prior. We just follow normal distribution, some mu and gamma to control uncertainty. So this is you have a lot of variation of this one, but most of the time people use this kind of baseline framework with a lot of variation. So they can put different prior. It can be beta, Gaussian, whatever prior. So usually what happens is we have the data and we update the prior distribution to get the posterior, the conjugate posterior. We sample the weight vector from posterior and we just select the arm, we maximize this one. So we calculate for all the arm basically and we just take the maximum. Of course you have a bit of variation, but that's the overall picture. So of course computation much more simple and everything is just put into the choice of the prior distribution and the choice of the context vector. Okay. So yeah, so I go a couple of examples. I mentioned this one, the App Store one. If you go on front page of most of the e-commerce website, mostly kind of Bandit, this one in Japan, and in Japan, in my case too, we are using Bandit for geo-spatial targeting. Or maybe for people who doesn't know Japan, there is a Yahoo Japan. Yeah, I suppose nobody really knows Yahoo Japan, but it's number 2 traffic in Japan. It's just behind Google. It's above YouTube. It used to be number 1. Yeah, I think Google, of course, made a lot of progress. We can use yes, this kind of bandit for geo-targeting too, and use for Amazon. If you go on Amazon, they will use a lot of bandit. They have a lot of paper on this. So I will go into quickly in the evaluation method. It's relatively interesting. So technically, you have 2 types of method. It's called offline, and we use the past data. We evaluate the model using the past data. It's called offline. And online, typically, it's the question of Gauthier. We put in production and we see how much they bring in the revenue, number of click or number of dollar revenue. And basically, we do a A/B test. We do 2 versions of the algo, and we measure which one has the best revenue and do statistical analysis of this. Is the goal of the offline evaluation is to correlate with actual numbers online. It's called offline evaluation. In reality, you have a lot of gap between past data and online because conditions are different. And you have offline method means that we have different type of offline method. I will just focus on this one. It's called policy evaluation. Just to sorry. So I will just explain one method of offline. You have a lot of them, but the main idea of offline method is you have your past data using a different algorithm. So you need to resample your past data. And of course, it's highly biased to your past algo. In order to unbias your past data, you use some weight. Typically, you use the inverse proportionality score to unbias your past data. Because you use with different algo. And if you unbias your past data, you can have, let's say, good sample data, and you can use those one to calculate the new metrics with the new algo. You have a couple of research on that topic, especially if you have a lot of bias of them. Technically, just use the past data direct method, you have high bias. And you have maybe variance low. So you have a lot of method to try to use the past data to estimate the online data. IPS is the baseline method. It is a very active topic of research for people, and it's quite interesting topic.
So Kevin, another
Yes.
naive question for me. So the last 2 slides you mentioned, it looks
Yes.
very much like, HFT trading in traditional financial markets, where, it's you have the two problems. One, there is the backtest and there is a discrepancy, and the discrepancy can be triggered because yourself and other participants used a previous algo, and this previous algo modified the universe of what you have recorded, the past data. And so
Yes.
when you want to backtest a new algo on this past data, you are not sure of what you are measuring. So here you are showing the solution, the literature on, I guess, people that work on ads. But
Yes.
since you were in finance before, did you also encounter that in finance, or is there a relevant literature about that?
I think that's a very good question, in fact. A bit less fortunate. Yes, I think that's a very good question. And yeah, I think can be those kind of technique can be reused in finance to have better backtest. Probably because the problem in finance, but you have different way of doing backtest. You have just the historical backtest because people just want to show that in the past it just works. And you have more the scientific backtest. You do kind of Monte Carlo synthetic data. So you do synthetic data and you estimate your quantile on the synthetic data. And maybe it's more relevant in high frequency trading because you can have more synthetic data. I was less in high frequency, so I know less. I suppose people are using this. I'm pretty sure if you go in the hedge fund or people have a lot of resource to investigate those kind of sampling method, resampling method, probably they will use resampling method. I don't know which exactly, but I'm pretty sure that because in the end, as you said, you have the bias of the previous algo. In general, the hypothesis that people say that the algo doesn't affect the market, but in fact, it affects the market. And probably we need to remove this bias. Yeah, I think I'm a good research topic. We do it in ads more because it saves cost. Because we try to remove A/B test. It costs a lot of budget, so that's the reason. But I think that's a good question, a good topic to probably investigate for people.
Got it.
So I just go. I don't know how much time I have. I have a bit of time, so okay. So I don't have to speed up too much. Okay. So we mentioned a bit the evaluation method at the end, a bit more. So happy to discuss more on that topic in the question after. Okay, so and we're going to more the practical part that personally or in general people have to face in that field. The recommendation is typically the scaling and latency. So typical requirement in ads, we have let's say 50 million users with a lot of query per second, and you have a big catalog, typically in Amazon, or you have high billion items, and other e-commerce too. And we have to serve the final user in 50 milliseconds. So maybe model inference has to be in 20 milliseconds. So in fact, we have a lot of users to serve in the same time with a very big catalog. And of course, we don't have so much time to run prediction, whatever prediction. It's a real challenge when we try to personalize. Personalize means you should buy, let's say in Amazon, some shoes, some iPhone, some coat. So you have all your user history. And typically, we can predict at some extent or try to approximate that you will buy maybe some scarf soon and whatever things you may have interest. So because you have a lot of users, you need also to evaluate all the items technically. And so you need to have all the users times all the items. Which means you need to calculate all the score, very high number of score on the daily basis and on the real time. That's the main challenge that people have. And that's the reason why people use less the real big reinforcement learning modeling because the high cost in inference. One of the goals is to reduce the cost. So I put just a scheme. Here is the latency to serve. If you go to 1 millisecond latency, of course, your cost we skyrocket a lot. It impose very hard constraint in model complexity in data process. And a lot of effort is spent in model inference. That's why you have the TPU. AWS also has their inference here. People can check. And we need to compile native code, a lot of things. And we need to spend time also to design system to have distributed compute to distribute the latency in different parts. So I wanted to highlight this part because this part is something not always discussed or mentioned, so people maybe not aware. It's same when you have a higher number of users, when you have a gigascale data, well, you have nothing to do because you can just use your laptop. If you have terascale, well, you add more machine. And at some point, even you add more machine, you need to have some paradigm change. Just adding more machine will not work, so you need to change completely the data infrastructure. And on top of this, what happens when we do the model part? Not all model can scale. That's one issue. And not all model is cheap enough to scale. People maybe is aware about the ChatGPT that everybody is talking about. Microsoft is spending time. In fact, ChatGPT is highly costly to use. They use a lot of budget for this. And that's one of the reasons they cannot put to every user. So also now you reach some level, you will it will bring a lot of restriction of the modeling. In fact, it forces people to simplify the approach and to have much more simpler computation. Just my 2 words on that topic. The data regime will determine the scaling in latency. And the scaling latency will also determine the scope of the model we can do, what kind of things we can do. Especially what we cannot really do, in fact. And another part is you have enough data and more real-time data. You can, at some point overcome some model weaknesses in terms of bias and bias. Not always, but you can compensate, in fact, by even with simpler model, we can do reasonable good level of prediction or recommendation because you have enough data or data in real time. And those kind of challenge is was the more tool for reinforcement learning because we need to have additional pipeline. And that's a part. So I think that's something that people don't mention so much, but I think it's kind of a bit useful to keep in mind. So just to add on top of this, kind of a bit simplify data pipeline, like the feedback data pipeline. And I put this data stack as a big because as soon as the data become bigger, from spending more time on the model, we have to spend more time on this part because you have a lot of distributed data, a lot of platforms, so you have to connect everything. And one of the issues for reinforcement learning or Bandit, you need to have the feedback loop back. So you have the roll, the loss, the click, everything. You have user behavior, and you need to have this user behavior back to the model. It looks simple, but aligning all the reward in the future, the action for every user. You can imagine millions of users, millions of items, aligning everything in semi-real time. Make things very complex. So in real world, in fact, we need to balance back more in the kind of data part. Another part that I mentioned, that real world part, typically when we do the research and dev mode, typically I use PyTorch, so I mentioned PyTorch. We have the eager mode, we can just evaluate on the machine, and also it's very good because we have the flexibility of developing new model. It's good for research. And PyTorch is very flexible. But in real world, in fact, Python can be slow, and slow means cost money to use it. Latency is scaling, and we need to compile those models. So you have now a lot of activity of the compiler, Python compiler, you have TVM, AWS too, Microsoft too, you have TypeScript. So I personally spent quite some time to refactor some PyTorch part. Reason why, because the compiler in PyTorch is called TorchScript, is designed primarily for NLP and computer vision, convolution, attention, you optimize a lot. It's not designed for reinforcement learning when you need to do a lot of sampling process, typically the Torch distribution. Even now, we need to rewrite some custom operator for the sampling. You have also an implementation challenge, which is a part of the kind of reward part. Okay. So I have a bit of time, so let me just spend a bit of time on the geospatial data. Maybe new for most of the people. So one use case, typical use case in geospatial data, you have some location here. I put the map of Tokyo. Sorry. And you're either searching, looking for some shop, night shop, for example, night. And you have a commercial center and you want to have some night shop. In geospatial data advertisement or geospatial data, you have two apps to retrieve location. One is a spatial nearest neighbor that you want to have shop around where you are. So it's typically geospatial index. And you have a geospatial index, quite key, you bear Google. You have a couple of them. And you have another one, which is the semantic nearest neighbor, which is typically the NLP, the embedding for the NLP. So you have two apps. So you want to have shop closest to you, but with night brand. So you need to do the search into two directions. And what happened when we do nearest neighbor? That technically when people use a face, does not work when you have two apps of direction. Usually you have one distance metric. Typically either you have the embedded metric or the whatever metric, but usually search in one direction. I explain kind of the problem. For example, if you want to search a nearest shop for a fashion brand Nike, if you take the top closest location, you can take the top 101, and you can have none of them can be Nike shop. If none of them are Nike shop, you need to retrieve 100 more. So yeah, kind of uncertainty. It's okay for one user, but if you have millions of users, all in real time, you cannot have this approach because you had a lot of latency, a lot of kind of extra compute. And what I'm trying to say, if you use a standard approximate neighbor search, like the FACE, it does not work well, and you need to have on-the-fly filtering, and on-the-fly filtering is kind of problem filtering on the graph. The interesting problem is technical, so it's kind of challenge, additional challenge we have to do with geospatial data. Just to mention. Okay, so I'm going to the end of this presentation. I hope it wasn't too fast. So just try to mention a couple of topics that researchers spending time on this, either in conference, mostly in conference or university. It's called OP. OP is offline policy evaluation. This question of Gauthier is to use the past data to estimate the performance of new policy or new algorithm, and to check if this evaluation is in line with the real evaluation in life. A lot of active research topic I mentioned to reduce bias and variance on those estimators, because they are still very high, and especially in reinforcement learning, you have a lot of noise. So people can check the HTML paper or the paper. You have at the same time offline reinforcement learning. If people are really have interest, we can have a look at this guy. I just copy pen in the chat so people can have a look. He has very good quality on that topic. It's very active research topic, but also very difficult. Technically, what reinforcement learning trying to do is try to build internal representations of the environment. So you can sample better the environment. And the problem of doing internal representation is you need to include the counterfactual, the event that the action you did not take, but can have high impact. So in terms of modeling, you need to have a kind of more word model, and word model can be very, very noisy in some situations. So, but it's very interesting topic. And I mentioned last topic, which is very active in the field, is the causal method for ad and recommendation. So we use causal method in different ways. Not all people, but it become more and more kind of active topic. One is to analyze A/B test. So A/B test is a randomized experiment. And as you randomize your experiment, you can have some causal graph. Technically, you can have estimate. You can estimate of the causal graph, and you can estimate the causal effect of action. Technically, you have AT and all this kind of estimator. Typically, the randomized experiment analysis is used regularly. And also used for counterfactual. If you have Bayesian setup, as we have the probability of all action, it makes things easier to estimate some probability of action you did not take and it include in the causal graph and have some estimate of the treatment effect. There is another class of problems called causal reinforcement learning. Is a more class of problem. Technically, we take directly a causal graph. We take the DAG directly as the input. So we take the DAG as the input as a node of the technically instance of we have let's say a graph, a DAG for user buying some item on Amazon, for example. So you have all the causal node that is user age of the user, salary of the user, if user buy this kind of good in the past, how many purchases he did in the past. So we have everything in the graph, in the DAG. And we can have some kind of bandit or reinforcement learning to find the best sequence of interaction on this graph to maximize the reward. So it's a kind of reinforcement learning with directly on the predefined graph. And is allowed to have more clear estimate. So one of the topic. If you go on the conference, probably this topic is one of the most
The topic. Yeah, I see that causality is in the mind on many people in finance, in ML. But what's your take on, because we can feel you have lots of practical experience. So is it some technique that is for now the dream of academics, or in companies you think they manage to really improve, make money with using the intervention on the DAG, and how do they find the DAG in practice? Is it you crafting it? So what's the current
yeah, no, this
state
one
like?
is still research. This one is research.
Okay.
This one is research. The causal bandit with kind of specific problem. The causal method for analysis randomized experiment is actively used because we need to have some estimate.
Okay.
So in fact, causality is one word, but it's very large field with very different components.
Yes.
The one actively used is the one for with randomized experiment estimation. You analyze randomized experiment. Okay, so I'll finish most of them. Maybe before I go into the comment, maybe people may have some question. I think it's quite long. I hope I haven't lost too many people. Sorry.
It was a very comprehensive and eye-opening tour on Bandit. So personally, I didn't touch that since my master, which now is more than 10, 15 years ago. So please, people, if you have questions for Kevin, now it's the good time for the people still awake. I know it's late.
Yeah,
but
sorry, it's a bit long, but I hope.
no
So I
worries,
give
no
you
worries.
my email. People may have some question directly on my email. Feel free.
Okay.
I will go into the comment. So I will go is much more personal comment. It's not necessarily back with it's more personal experience comment. Yes, especially for reinforcement learning. It works. And people are show it. It works for to solve very high dimensional problem, space, AlphaZero, or lot of example. But need a massive simulation sample. Reason why? Because the model has to modelize, make a implicit model of the environment by sampling. We sample it from incomplete representation of the world. It can be very noisy and very incomplete. Another issue I find in reinforcement learning is the lack of transfer learning component. What happens in most of the model in reinforcement learning, we need to retrain from scratch. Most of the, not all, but let's say most of the time. As soon as you have new environment, new domain, you start from zero. If you train it for 1 or 2 days, you have it. We lacking transfer learning. What happened in computer vision and NLP recently, more over the last year, we have transfer learning, that you have a big model, and you can reuse the big model much more efficiently because you have some kind of transfer learning. You can fine tune the big model, you have some building block, and you renormalize a bit the kind of complexity into building block and make more, let's say, more reasonable computing. I think when reinforcement learning will get some component of kind of transfer learning, either between the domain or between the maybe between the domain, probably reinforcement learning will be much more, let's say, day-to-day usable, much more. The usage gap probably will reduce a lot. It's kind of my personal comment. And another comment, because I suppose most of the people are here in suppose in finance. So my opinion between finance, maybe big data, or another part in finance, usually people have to deal with lack of data. It's not lack of data, it's more the state of lacking data. Always you have kind of state that we don't have enough data. That's more the point. Much more because the environment is uncertain. You are highly non-stationary environment, and sometimes makes things more better to estimate the uncertainty itself rather than the prediction itself, the actual estimate. That's why having simulation and something help to have estimate of the uncertainty. So my opinion, finance need to deal much more with the state of not having enough data a lot of time. Whereas like ads or recommendation, like big data area, sometimes we have too much data because we have too many users. And the problem of having too much data, you also have a lot of noise of them. One of the goals is just to transform the data into a usable form, something that we can have more as a human level, let's say, much more smaller size data. So a lot of solutions are designed to handle the too much data. So typically the reinforcement learning we prefer Bandit because just easier to manage higher volume of data. And also reason is the offline method might make more sense is probably in the recommendation and as the environment is a bit more stationary than in finance. the behavior of people, doesn't change so much from one day to another. If people buy shoes, maybe next day he will buy shoes or whatever. It's those kind of personal comments. And I think that's pretty all. Not sure if people have questions. It's a bit late. So if you don't have question, if you have some question on research and topic or about geo. I'm not sure about geo, but whatever research topic, feel free to send me an email. If you visit Japan too for conference, happy to discuss with some people